Hello again. Now in Climate Science 1, we looked at one reason why there's no greenhouse effect, and in each video, which I'll try to upload one every week, we're going to look into all the reasons why there's no greenhouse effect. In other words, no surface enhancement, no surface thermal enhancement due to so-called greenhouse gases. And of course that means that CO2 actually does nothing at all, and it's nothing to fear. CO2 cannot cause climate change unless it causes global warming first, and I'll demonstrate that it doesn't cause global warming, not anomalous global warming, and I'll detail later in another video what I mean by anomalous. Okay, so in this video, which is the second in the series, we're going to look at why there is no extra warming to explain through the addition of CO2 to our atmosphere. In other words, all the warming that we've seen since 1690 has been pretty much natural, and it's easily explained by climate cycles. Now in this video we're going to go into the science of climate cycles a little more, quite a bit more really, which has not been covered by the IPCC, understandably, because it contradicts their ideas about CO2, so they haven't included it in any of their reports. They basically include just one climate cycle, or one solar-induced climate cycle, if you like, which is the Schwab, the common 11-year solar cycle. And the effect of that is every 11 years we get a 0.1 or 0.2 degrees of warming, and then the cooling again 11 years later. So it's not really affecting the temperature of the surface of the Earth in a net way over time. But I'll demonstrate there's a lot of other climate cycles that the IPCC have totally ignored. Now, we've got to go back a little bit in time. First, as you know, the Earth's 4.6 billion years old, but we're only going to go back 550 million years to start with. That will give us, sufficient sort of idea about how the climate changes over, say, tens of millions of years in time scale. So here is a record of the Phanerozoic climate change regarding temperatures taken from an oxygen-18 isotope. We won't go into too much detail on how they get this record, but its a proxy record is just a measure of the past, and generally in terms of either temperature or carbon dioxide atmospheric concentrations, so that we can know, we can compare the past to the present. And knowing the past really helps in determining whether the present is unusual or usual. So, as you can see with this graph, temperature goes up and down on sort of, or you could say, it goes up and down on 30-40 million year timescales, and this is linked, I'll explain later about this, but this is linked to the solar system bobbing up and down through the disk of the Milky Way. So this is a long-term climate cycle, a 34 million year climate cycle. And we see it here quite clearly. Now, through most of the last 500 million years, as you see here from the graph, the Earth has been warmer, much warmer than it is now. We're in fact in an ice age. And really for the last 100 million years, as you see here, there's been a steep descent in the Earth's temperature. That's not just related to us going up and down through the plane of the Milky Way, it's also related to us going through spiral arms. We're currently going through a spiral arm in the Milky Way called the Orion spiral arm segment, We won't go into that in detail right now, but what that does is it causes more cloudiness on Earth, which causes obviously cooling, because clouds reflect solar energy on average, and more clouds on average causes cooling. Okay, so that's the framework we're looking at. It's cooler now than it's been for most of the last 500 million years. That's our starting point. So we're in an ice age right now. As you see, there's been 4 big ice ages in the last 550 million years. Now next we'll go a little closer to the present. We'll look at the last 65 million years. And again, most of the last 65 million years has been much warmer than it is right now. So even compared to the last 65 million years, we're in an ice age. We're much cooler. When you get a lot of cosmic rays hitting the Earth, what that does is create more cloudiness. So more cosmic rays, more cloudiness, a cooler climate. See here, I've noted on this graph starburst in the Milky Way 15 million years ago. And when that happened, the Antarctic reglaciated. It did glaciate about 35 million years ago, and then thawed about 22 million years ago. And then when we had the starburst in the Milky Way 15 million years ago, the Antarctic reglaciated, and it's been total ice cover over the Antarctic ice cap. The Antarctic ice cap's been there that long, in other words, for the last 15 million years. And that ain't gonna melt. I can tell you that right now. Okay, and we got a further rapid glaciation about 3 million years ago when we had another starburst in the Milky Way close by. So again, starbursts are when there's a massive amount of star formation within our Milky Way galaxy, and that creates a lot of cosmic rays, which creates cloudiness. So we'll move a little bit. Again, we've had that descent into ice ages. It's getting cooler and cooler. So we'll look at the last 5 million years of climate change from sediment cores here. And basically the last 3 million years, it's dropped below the current temperature for most of the time. So it's only in the last 3 million years where it's actually been cooler on average than it is now. So for nearly all the last 500 million years it's been warmer. It's only the last 3 million years where it's been cooler than it is now. And the Earth has started 3 million years ago to be dominated by the 41,000 years Milankovitch cycle. And in the more recent 1 million years, the 100,000 year Milankovitch cycle, which is related to eccentricity, has taken over. Now, eccentricity is when the Earth's orbit goes like this. It changes from being circular to egg-shaped over a 100,000 year cycle. We'll come back to that because eccentricity is very important. At the moment, the Earth's orbit's fairly egg-shaped, and what that does is that when we're close to the Sun, we get, of course, more solar energy than when we're at the outer part of the egg-shaped orbit. When we're further away from the Sun, we get less solar energy. And that is a big difference. It's really in July when we're the furthest from the Sun, and in January when we're the closest. And the difference is, at top of atmosphere, is 92 watts per square meter in solar insolation forcing. So you get 92 watts per square meter more in January, top of atmosphere, than you do in July. Now, you'll notice that there's not a big variation in the Earth's temperature between the hemispheres. And we'll come back to that as well. That is also really important because it means that basically clouds can change that amount of forcing. It can change that extra 92 watts per square meter of forcing and eliminate it. And that's essentially what cloudiness between the northern and southern hemisphere do. I'll show. Here's a paper in reference to that. You can look it up. Okay, we should just touch on a little bit the climate cycles that I've identified from the literature. 16 different ones I've found in the literature. Some are really important for the current series of climate changes that we're experiencing. And yet only one of them, that is the Schwab, the 11-year sunspot cycles, which is tied to Jupiter's orbit and the barycenter motion of the Sun. That's the only one that the IPCC recognizes, basically the only one it mentions and uses in its reports. That is a fatal mistake that they have made. Okay, now the important ones here at the moment for us are the Bray, the 2300-year Bray, which underpins the current climate that we've got, and the Bond cycle. The De Vries cycle is also important, the Gleisberg, and in particular, in terms of the late 20th century global warming we've experienced, the Yoshimura is the most important one. It's a 61-year barycenter cycle of the Sun, tied to Jupiter and Saturn's tidal beat. It's because the Sun has a motion around the solar system's barycenter with a 61-year cycle. That causes changes in solar activity, which causes changes in climate on Earth on a 61-year cycle. It's extremely important. So every 61 years you get a warming and another warming and so on. And these warmings peaked in the more recent period in 1880, 1940 and 2002. At the moment we'll go straight on to the underpinning of the current global warming that we're experiencing. We've gone back millions of years, but now we're just going back 1,000 years. 1,000 years. So we're well within the current Holocene period. We experienced the coolest part of the Holocene, that's the last 10,000 years period, in 1690. That was the very coolest it's been in the last 10,000 years. And now we're sort of, most of the Holocene was warmer than it is now, but we're a little bit warmer than the coolest part. We're about 1 degree warmer than the coldest part of the Holocene. So here you can see a graph starts in 1150 AD and goes to 2150 AD. And you can see solar activity being portrayed here, in particular through sunspot activity. That's the red line. And of course we know what it'll do in the future pretty much. So it's projected into the future. Astronomical phenomena are predictable. In black, we've basically got the measured temperature on Earth's temperature. And you can see that the Earth's temperature tracks solar activity perfectly, and still does. This is one of the places where we're looking for an effect from CO2, and we can't find it. So, if we go back to the about 1200, we had the medieval warm period. You can see there on the left. This is work by Steinhilber in 2012. You can look this paper up as well. And then we had a period of quiet solar activity during the Wolf minimum, and then a short period of warming around 1400. And then we had the Spora minimum, low solar activity around 1450 to probably to 1550. That was a little ice age we had there. And then we had a slight warming around 1600, and then we descended down to the Maunder minimum, which was, as I said, the least solar activity for a very long time, for thousands of years, and there was almost no sunspots seen on the sun for a very long time. And we had ice phares. We had very cold conditions on Earth. These frost phares and ice phares were very unusual for England, but they happened in the 1680s, 1690s. So here's a newspaper story about this in the 1680s. During the Dalton minimum, there was a further freezing of the Thames River in the winter of 1813-1814. But there's been no freezing of the Thames River since then. That was the last one. And I don't think we'll see the Thames freeze again in the next few hundred years either, because of the underpinning of the present climate by the Bray and the eddy cycle. Now, the solar activity record can also be, the proxy record can also be checked against things such as we got the last sort of 4,000 years. The glacier on Greenland has retained its temperature for these thousands of years, and all you need to do is drop a thermometer down there, down a hole, and this is what you get. This is work by Ali, published in the year 2000, and it records all the major changes that we see in the solar cycle record. Now, at the moment, we've got the modern warm period, as I said, which started in 1690, as you see here. And where it says now, that's pretty much where we are now, at the peak of the modern warm period. And it's going to get cooler over the next few decades. And looking further forward, over the next few hundred years, it's going to get cooler. Because eventually we're going to leave the Holocene, and we're going to fall down into another ice age. We're pretty much at the end of the current interglacial, and when we do descend into the next ice age, things are going to get pretty nasty. Okay, what I'm trying to show here is that there's no extra warming to explain. So there's no room for any supposedly global warming from carbon dioxide or other greenhouse gases. I'm not showing you any fake hockey sticks here. This is the real science. Now here we've got a non-tree ring proxies of temperature, global temperature over the last 2,000 years. This is work by Lowell, published in 2007. Now you'll notice that everything I claim, everything I show you, every graph has a reference. So please, if you want to, you can check these references. This non-tree ring proxy, unlike man's hockey stick, this clearly shows the medieval warming period, the Little Ice Age, and the current warm period called the CWP, which started about 1690 and is continuing today. And we hope it does continue, because we love warm weather and we don't like the freezing cold ice. Here we've got work by Soskin, published in 2007. And it's really the isotope of carbon-14. So it's a proxy basically for solar activity. That's what it is. It shows you how much solar activity there's been over the last 11,000 years. So 11,000 years ago, the solar activity was very high, similar to what it is now. And in between, it's been much lower. So we have now got the highest solar activity, or I should say we had in the late 20th century, the highest solar activity for 11,000 years, according to this study. And to another study I've seen, the highest for 4,000 years. So it's definitely the highest solar activity for thousands of years in the late 20th century. If that's not going to cause warming, I don't know what is. And just for good measure, here is sunspot number record, published by Ledecky in 2011. and another carbon-14 isotope proxy record for galactic cosmic ray flux of the last 1,000 years, demonstrated the medieval maximum, spora minimum, Maunder minimum, and modern maximum right now, showing the massive increase in solar activity since the year 1700. Now we've reached the nowhere near famous enough six European city study by Ludecker, 2013, which shows actual thermometer measurements from 6 European cities going back to around about 1750, 1780. And you can see that the temperature started high around 1750 to 1800 and then went low down to about 1875 minimum and back up to a warming around 1940, then again in 2000. So again, what we can see here is climate cycles. The Swiss and de Vries climate cycles, and we can also see the Yoshimura. So we've got the 200-year cycle and the 60-year climate cycle. And you've ended up with basically no net warming from 1800 to 2000 across Europe. And Ludecky also pulled some real information out of these graphs about climate cycles. Now the really important ones for us is the 248-year climate cycle, the de Vries Swiss climate cycle, that's what it is, the 80-year climate cycle, which is the Gleisberg, and the 61-year Yoshimura cycle. These three are the main ones that we need to concentrate on and which dominate the climate over the last 200 or 300 years and still dominate it today. And finally, this is the graph that Ludecky produced in his study in 2013. He showed that there was, once you put these climate cycles together, which is the red line, and you compare it to the actual temperature measurements across these 6 European cities, the black line, there's absolutely zero extra warming to explain. So there's no room for any CO2 warming across Europe in the last 200 years, last 250 years. I may as well throw this into the mix as well. This is work on Neptune by Sromovsky, 2003. What it shows is the period of 1915 to 2000, how Neptune has brightened over that period. It's because of solar activity. The increase, this is just more evidence for the massive increase in solar activity that we've had during the last half of the 20th century, which, as I said, is the highest for at least 4,000 and possibly 11,000 years. And so there's evidence from the other planets as well, but I'm just picking on Neptune here. You can see how the top there, you've got the brightness of Neptune, which has even followed the Earth's mean temperature anomaly. Neptune's got warmer from 1910 to 1940 and cooled down to 1975 and then warmed to the year 2000. Exactly like Earth did and exactly according to the TSI from the same study. So it's all falling into place and nothing to do with CO2.